Hi guys, my name is Valerie Simonis. I'm a PhD student at DePaul in computer vision and data mining. And my main sort of interest for this final presentation is to look at sort of the cooperation between AI and computer vision and how computer vision topics can be used in AI. And a really good application for this is autonomous driving. So we have, certain things that we've learned about in AI, and I'm going to augment, some of the things with what I know from CV, and it's really particular to the perception of the environment and the vision component of an artificial agent. And specifically, self-driving cars are robotic intelligent agents, and we've mostly been learning about sort of regular artificial intelligence, and in the robotics context, there are a couple more considerations. And so, in order to survive in its environment, an intelligent robot needs to have similar levels of AI capabilities, but also have energy independence, an ability to diagnose its own state. So, because the state within an environment is, physical, it has to have a different kind of understanding of its environment than some of the examples that we've seen. It needs to be able to evaluate its perception abilities and react properly to an unknown situation. And not on this list is also the requirement that it needs to be able to learn from situations in order to, progressively handle these unknown situations better and better. Now we can evaluate these self-driving cars using, some of the framework that we've discussed in AI, including looking at what the environment might be, what percepts, sensors, and actions might be. And also I'll touch briefly on some of the internal workings or some of the considerations of the decision-making process for a self-driving vehicle. But there's not a lot of information about the internals out there. So in terms of the environment, it is split up. So I read a really great paper that explained a lot of the self-driving car stuff from an AI perspective, which I reference at the end. And so that paper splits up the environment into 4 levels. You have traffic, which is the top layer, and that includes all sorts of objects and obstacles that are currently in motion or capable of it. So think about other cars, pedestrians, cyclists, or parked cars that are currently not in motion but are capable of it at sort of any given time. There is a level of priority rules, which is shown here, and there you have traffic lights, road signs, and based on that information, you also have sort of a set of possible instructions that follow given the rules of the road in whatever country you're in. And then you have sort of the stationary obstacles, which would include buildings, ramps, or ramp guards, and then sidewalks. And then you have a layer of geometry, which is essentially the physical map or the lanes that exist on the road that you're driving on. And so this environment gets captured and seen by sensors, which can measure things like acceleration. So internal to the car, a little bit more boring, you have acceleration, rotation, and distance, and that's pretty standard. And then more exciting are the exteroceptive sensors, which can include video cameras producing images, lasers, GPS, and so the combination of video camera, laser, and GPS is often referred to as LiDAR, which is sort of a singular machine or sensor that does all of those tasks at once. And then there's another category of sensors or information that you can gather about the environment that is communication-based, and that's using other vehicles, the infrastructure, or sort of information about pedestrians as from a network standpoint of all these things are communicating with each other and helping each other localize each other in the greater environment. Now, in order to sort of parse all these sensors and come up with good locations for both the car and sort of the obstacles and objects around it, that's when computer vision comes in. And that's where you have to transform these sort of digital inputs into more tangible physical locations in the real world. And that's essentially what computer vision does, is transform sort of image or point cloud data into a usable information about the position of something within the real world. And so, your input can be either point cloud data, like this is an example of, I think, from the Google car, the LiDAR, or just straight up image data, which is essentially a matrix where each entry is a corresponding intensity value that, in the grayscale format, white would be 255, and you have different shades depending on what that value is. So computer vision, the first task is always image processing, and that's mostly sort of, making a couple changes to the image in order to get better features or features that have different meaning. And specifically, with LiDAR data, similar to motion capture data, the LiDAR gives points that are precise up to 11 centimeters, which is really quite precise, but is capable of delivering noisy points and is capable of also producing points that are very, very dense and that are, the numerosity of which is hard to kind of make decisions about what the situation is. And so there's, processes and techniques to filter noisy points or to only keep sort of points that are important to the task at hand. From either the image data or the LiDAR data, then you have to extract meaningful numerical features that you could feed then to some sort of data mining task. And traditionally, in regular computer vision or image processing, features are corners, edges, blobs, regions, or points. And for these types of features, then you extract information about them that relate, in terms of regions. If you get a region of interest, like say you find a pedestrian, then you want to know maybe the size of it so you can figure out how close or far away it might be. Similarly, you want to maybe get texture information to figure out if, a little patch is grass or road. These are just a couple examples of meaningful features that you could extract about a scene. And then once you have all of these features, you would use data mining or pattern recognition, training on examples to detect objects. So to say, like, there is something, at 35 degrees, 10 meters away. And once you detect an object, to recognize it and say, okay, that something that I detected is actually a pedestrian. And there's a task of image registration of, given two sequential images, what points correspond to each other. Similarly, from a LiDAR perspective, you want to keep matching your point clouds as you go to render a 3D world. And then, really important to the self-driving car example is, the 3D geometry and scene reconstruction bit of it. So creating that environment in a realistic, accurate way. And then doing motion analysis or tracking on elements of that environment that may be obstructions or things you could possibly hit. So once you've done all of that, those vision tasks, and you have a good sense of perception, you want to make a good decision of where the car should go. And one of the main points of the paper that I read is that a lot of these processes take a long time and are quite involved, and really aren't always completely accurate. And so there should be a supervision layer in this AI that can express the uncertainty or can evaluate the uncertainty of its perception, and from there dispatch resources to the level or layer of perception that is most important, and that gives, the better impression of what the environment might be. And so that was a really kind of interesting insight from that paper. And also another suggestion that they had for sort of putting all of these features together, or to sort of make things a little bit faster in computation time, is to offload some of the tasks, or to have, a vehicle to vehicle system where vehicles handle different, there's a sort of dispatch situation or a distributed network of AIs kind of helping each other out, if their neighbors are in the vicinity of each other, to get good information about the environment. And you can distribute some of the work to the infrastructure as well, and pedestrians. You might be able to do GPS localization using phones, and so you don't actually have to find them physically in an image. You can just know where they are and track their movements, and which is kind of interesting. And so once you make a decision about what a path might be, so where you are, depending on where you are and where you want to go, what navigational decisions to make as a self-driving car. Really, you have very simple actuators. You speed up, slow down, turn the wheel a couple degrees, left, right, or hit the brakes depending on what the situation might be. And those actuators are pretty commonly manipulated in, say, like cruise control situations, for example. And finally, hopefully you put all these things together, all this information together, you make decisions using uncertainty as sort of a guide in what information you can and can't trust. And ultimately, the self-driving car brings itself to its desired destination, has followed the rules of the road, and did not hit any moving or stationary elements of the environment. So this is a really interesting paper that I read that essentially is most of the information that I got for this presentation is included therein. If you have any questions, feel free to send me an email. It's located down here. And I really hope that you enjoyed it and learned at least a little bit about computer vision and in the context of AI. Thanks.